I feel pretty, oh so pretty. Okay, so we are doing example problem number 7 for electric potentials. There's the bell. Goodbye. Now, what we're looking at here is a 5 microcoulomb charge at the origin. So here it is in red down here. And a point charge of -2 microcoulombs on the x-axis at 3 meters. So over here, and we've labeled that 3 meters with that green bracket right there. We'd like to find the potential difference, the voltage, resulting from these two charges between a point at 4 meters away on the y-axis, so that's the green x up here, and then a infinite distance away. So that's what we're comparing this to. So how do we do this? Well, since we're looking for electric potential differences, voltages, we know that we can just take that the sum of the voltages from these two charges, the 5 microcoulomb and the -2, we can just add them together. Okay, and if we have both of them, we're good. We also know that for a point charge, the voltage is just equal to kq over r, where we have to put in the positive or negative for the q. Even though voltage is a scalar, it has a positive or negative quantity to it. Okay, so I know k, it's Coulomb's constant, 9 times 10 to the 9th. I know q, that's the 5 microcoulombs or -2 microcoulombs. And do I know r? Yeah, kind of, but sure. One of the r values is 4 meters, because that's physically how far away in a vertical direction the 5 microcoulombs is to that point in space we're looking at. But when we look at the -2 microcoulombs, this is the distance I want there. This is the r value. And we don't have that. Except we can get it. This is a right angle right here, which makes this a 3, 4, 5 triangle, which is really, really nice for us. Sorry about your ears. So with this, we have both of the distances for both of the charges. We have both the charges themselves, which means we can get both of the voltages. And since we're comparing these two potentials at an infinite distance away, which is 0, then whatever the potential is due to this kq over r equation, we just add them together, and we are done. So let's just get to it. Okay. For the first charge, we know the voltage is just k, which is 9 times 10 to the 9th, times the charge, 5 times 10 to the -6 coulombs, divided by that distance of 4 meters. Put that all together, and what do you got? Ooh, we're going to get some big numbers here. We've got 112,000... Oh, no, I'm off. That's 11,250. 11,250 volts. When we do this for the second voltage, for the negative charge, we have a very similar equation, k, which is 9 times 10 to the 9th. We have charge 2, which is -2 times 10 to the -6. We need the minus there to let us know this is a negative potential. And then divided by that distance, which is 5 meters. And when we do this, what do we get? Well, we get out of it negative, due to the negative, 3,600 volts. And now we have just the simple task of putting them together. Let's just sum these to get our total or net voltage. So that's 11,250 plus the negative, so minus 3,600 volts. These are all volts. And we get here 7,700 volts. And that is the final answer there, simply because we are comparing this to an infinite distance away. Remember, the voltage at infinity is equal to 0, so the difference, 7,700 minus 0, is still 7,700, okay? So that's it. That's the quick problem there. Voltages are so much easier than electric fields and forces, because before you were looking at this problem and you're like, oh no, I got to do sines and cosines and tangents and the triangles and the vectors. This, super easy. Just voltage 1, voltage 2, put them together. It's that easy. So I hope you enjoyed that. This problem is finished, and I'll see you in the next video for our last electric potential example. Until next time, adios.